Hi everyone, I'm Pranav, and today we're going to talk about how Databricks and a whole bunch of its customers are using Autoloader, a new structured streaming source, to ingest data at petabyte scale. So the first step in any sort of data pipeline, which we can see here from like a 10,000 foot view, is data ingestion. And here what we can see is what we want to do is take these input files, which can contain unstructured or semi-structured data, and put them into cloud storage. So let's say an S3 bucket, like our logs bucket here. And finally process that data into some final form. So this is where data ingestion comes in. And what a lot of our customers and what we ourselves at Databricks use is structured streaming for this purpose. It allows us to take data as it's coming in to get the freshest data and process it right away. And structured streaming has many facets to it that enables easy data ingestion. For example, it helps with restarting from failure and doing complex transforms. But there are actually still a lot of challenges associated with data ingestion. Let's look at what some of those challenges are here. So let's take the file stream source, which is an existing structured streaming source, and how it could fit into this kind of data pipeline we've been talking about. So let's take a look at what it looks like with the file stream source. So here we have that data pipeline using the file stream source to list files at an input directory. And what we do in structured streaming is we have this concept of triggers. So on each trigger, we would look at what files exist at the source and which to ingest into our final form. And those triggers can be set by the user at arbitrary granularity. So you can have trigger once to imitate something more like a batch workflow, to anything else that you want. So let's take a periodic trigger as in this example. So at our first trigger, what we would do is we would list all the files that exist in our log directory, and we would get back, say, a and b.json, and we would transform that data to our final source. The issue occurs on our next trigger. So at t=5, we list the whole directory again. And what happens is, though we do find this new file, which wasn't there before, c.json, we are relisting the files that we've already ingested, so a and b.json. You can see how this can become a problem once we have a directory with millions of files. Relisting that whole directory just to find a couple new files would be extremely slow and extremely expensive. And what I also want to draw your attention to here is we have this data structure to deduplicate files that we've seen so far so that we don't have duplicate data in our final source. So here, even though we're relisting a, b, and c.json, or relisting a and b.json specifically, we wouldn't re-ingest them because we've included them in the scene file paths map. But the issue is that the data structure here that we're using is an in-memory map. And an in-memory map does not scale, especially when it's in the driver, and once your stream reaches a certain load, you might have to increase the size of the driver, and it just remains a headache. Let's look at another challenge that often plagues data ingestion, and that challenge is schema. So the very first step where this kind of challenge creeps in is setting the schema in the first place. In the file stream source, you have to go in, manually infer the schema of the files that exist in your logs directory. So you would take, say, that a and b.json, and you would look in and find that they both have an ID and a name. And so you would think that, I'll set the schema manually for my stream to be ID as an int and name as a string. And you say, now I'm ready to go. I'm ready to get my data ingestion, kick it off. But just shortly after, what you end up getting is new data, potentially from some change upstream in your input files that isn't of the form that you expected. And this is extremely common. So what we have here is f.json, which contains a new column, age, that we weren't expecting when we manually set our schema. And what would happen normally using the file stream source is that you would just have data loss. There's no real good way to deal with this. You could build other pipelines to kind of look at what data has arrived and see if you're missing anything and deal with it at a later point. But this is ideally not what you want to do. And this isn't even a one-time issue. This is something that can happen constantly as your input data sources evolve. So this is where autoloader comes in. We took a look at all of these challenges that we've been seeing and built this new structured streaming source, which solves some of these biggest challenges, namely scalability and schema management. So let's take a look at how it does that. So firstly, we have this new mode called file notification mode. And to explain it, I need to introduce a couple of new concepts. So one is file notifications that are generated by cloud storage providers. So when a new file comes in, you can set up cloud storage providers such as AWS with S3 to generate a notification for a file as it's coming in. So in this case, as we're getting our input files, each time a new input file comes in, it generates a notification. And the other concept we have is cloud queues. Cloud queues are also provided by the cloud providers, which can store these notifications, something like this. So in this case, we have a.json coming in, and as it lands into our S3 bucket for logs, we get a file notification that's generated for that file, and we can put that notification into a cloud queue, which is going to be large and distributed and relatively fail-safe. And you can see where I'm going with this, where we can then use this cloud queue to pull whatever information or whatever files have arrived into structured streaming to finally process. And this is what autoloader does. And it's essentially consuming from this queue, and once the data has been processed, we're deleting those file events from the queue. And this completely oblivious the need for listing. So files are ingested as they arrive, which reduces the latency between file arriving to it being shown in your structured data as well. And the other issue we had earlier, where we had a map to see what files had already arrived, and it led to a whole bunch of issues with the driver sizes just to keep enough memory to contain this map. Instead of that, we're using RocksDB, which is a key value store and is used for point lookups, but is also scalable indefinitely. So with these concepts of file notification modes, as well as RocksDB for file deduplication, we aren't really hitting any scalability limits anymore. But you might be wondering, what if I don't want to ingest just the new files as they arrive? What about my existing files that already are in my logs directory, for example? And we've dealt with that here. And this is kind of the philosophy of autoloader as a whole, where we try to do the best thing by default, but always provide the knobs for you to adjust autoloader to your workload. So here we have what we call backfill. So a.json is a new file that's arriving into your bucket, but you already have this capital A.json in your cloud. And what we can do is include those existing files by listing them and ingest from that cloud queue we talked about before and put both of those sets of files into this internal queue from which we'll pull into RocksDB and so on into your structured table. So, and this is all done super simply. This is just a couple of options added and just a few lines of code to essentially implement this whole thing from RocksDB to the cloud queues to the event notification. So this is an incredibly simple way to implement an essentially infinitely scalable data ingestion workflow. Let's talk about another challenge that we saw earlier, schema. So the first thing was that we had this kind of annoying step of having to manually infer our schema before we can even get the stream started. I want to start my stream right away. So autoloader allows you to automatically infer the schema of the files that are there through some sample of the files in your bucket. So here we're going to automatically infer that ID is an int and name is a string, and now we're ready to go. But this is where we got stuck last time. We got this new column and we didn't really know how to handle it exactly. So what we do is you can use autoloader with delta to handle it in the best way. And what the best way really is, at least in some theoretical example, is that we want to ingest all our data without losing any of it to some location, let's say like a bronze table. It contains all the data in some structured way, but it's not necessarily what we're going to be using for BI or ML use cases. This is just a store of information that you can use for future tables to pull from and further refine. So that's why we have this schema evolution. So what we want and what we can do with Delta and autoloader is once we see this new f.json, we can fail the stream since we don't recognize this new age column. And on stream restart, what will happen is that our schema will evolve to contain this new column. Delta will realize that there's a new column and add that age column to its schema. And this is done basically automatically. If you allow, for example, Databricks jobs to restart your stream automatically, this can continue to happen as your input files evolve their own schema. Your final structured tables are also evolving with them, with almost like no manual intervention. And again, this is done super simply. You just set one option and this whole thing is done for you. So here I talked about one specific schema evolution mode called add new columns, where, like I said, we're adding any columns that we didn't recognize initially. But we have other schema evolution modes as well. So we have rescue data as well. So rescue data is similar to add new columns in the sense that it handles how to deal with changes upstream in your input files that you don't really anticipate. But this deals with a whole set of other issues. For example, data type mismatches, or if you have case sensitivity issues, all of that data would be quarantined into a new column called rescued data. So here in this example, when f.json comes in, we would have the record for ID 23 and name Alex, and then the age 31 would be contained in a blob in rescue data. And this gives you the flexibility of not saying like, maybe I'm too suspicious of evolving my schema all the time. And instead I want to just keep that data so there's no data loss, but gives me the flexibility to deal with it how I want. Maybe I don't want to evolve my schema. Maybe this is garbage data and I want to throw it out. Or maybe I do want to evolve, but only for a subset of columns, which you can do later on. Some of the other schema evolution modes we have are fail on new columns, which, as you expect, we just fail the stream and don't evolve the schema. But we do still capture data type mismatches, etc. And none, where the file stream source is kind of similar in that we would have data loss here. So if you want to use autoloader as you've been using your existing streams, this schema evolution mode is for you, while still giving you autoloader's scalability. Let's take a look at the demo and see all of this in practice. So here we have an autoloader stream that's reading from S3 and writing to Delta. And here we see some of the options in use that we've talked about. So one is the schema evolution mode, where we're adding new columns. So what this means is that as new columns that we didn't anticipate arrive, we will add those to the schema of the delta table at the end once they're ingested. And we're also using this file notification mode. So the file notification mode, this sets up the whole S3 event notifications, as well as the cloud queue that takes those notifications and puts them in the queue, from which autoloader will read the notifications in order to ingest the files instead of listing the directory each time to find new files. And we also have this interesting option called schema hints, which we'll come back to later. Let's see the stream running. So it's running and it had processed some files in the past. Let's just add some new data that's of the form that we've already seen. And what this is going to do is add a new file to S3. It's going to generate a new notification, which gets picked up by the cloud queue, which then gets picked up by autoloader, put into RocksDB, and ingested. And as we can see, this is working as intended. And let's take a look at what the data looks like. Here we can see just data that looks pretty healthy so far. There doesn't seem to be anything wrong with it. Let's look at the schema in particular. And here we can see that all of these columns are actually strings. And this is something that autoloader tries to do, is to make things very permissive and very non-error prone in the initial version, but allowing you or providing you knobs to give you the behavior that you want if you know what you're going for. So in this case, everything is inferred as a string by default. And so we don't get into any issues with inference where some columns may be inferred as longs versus doubles and so forth. So we also have this column called rescued data, which we talked about, and it captures all the data type issues that can occur where if something is inferred as a long, for example, and then along comes a float, that data would be essentially quarantined into this rescued data column. Let's take a look at what happens when new data arrives that isn't of the form that we expected, specifically in that there's a new field that we didn't anticipate. So we added that new file. Let's go up to our stream. And our stream has stopped with an exception for an unknown field exception, where we saw this column metadata, which wasn't in our initial schema, as we see here. And normally, if we were using the file stream source, for example, our stream would have continued without any knowledge of this, and we could have potentially lost out, or we would have lost out on that data if there weren't other mechanisms in place to catch this. So here, all we have to do is restart the stream. And because we set our schema evolution mode as add new columns, what this is going to do is take this metadata column and add it to the schema of the delta table we were writing to. And if we list the latest data, we can see that there's a new metadata column, which has the string column containing the new data that was in the file that we just added. And that's how simple it really is. But let's take a look at some other examples. So here we had inferred everything as a string. So let's take a look at what happens in this case if timestamp is, there's some data with a timestamp that's not of the correct format. So adding a new data, and let's take a look at what the latest data looks like after inserting. It's of this kind of format, which we don't really like. If you recall what our timestamps looked like earlier, they used to be this kind of nice format. This is kind of more scientific notation, which we don't really want. But since we were using strings, they were determined there was nothing to catch this from happening. This is where schema hints, which I mentioned at the very beginning, come in. Let's reset our streams and see how schema hints can help us out here. What schema hints are for these kind of cases where you know you are expecting data of some format specifically. So let's say I know that signal strength is a float, timestamp is a long, and metadata is a map of string to string. I can force my stream to, or force my schema rather, to have these columns and for any data that's coming in to be cast to these types. So let's restart the stream, and we will be able to now see that our table schema has changed to reflect this. So we have our signal strength as a float and timestamp as a long or big int, and metadata as a map of string to string. Now let's go back and add more data of this weird timestamp value. Right. And let's take a look at, here we go. So all this new data that is of this strange format gets put into the rescued data, since there was a data type mismatch between what we explicitly said we want and what we actually got. And this is really powerful because what it lets us do is really understand what's happening upstream in our input files, and also gives us the flexibility to deal with it how we want later on. If we deem this to be just garbage data entirely, we can discard the whole row. Or what we can do is figure out some kind of logic to insert these timestamps in for our later tables that might be more refined. Let's take a look at also the metadata column. Now that we've added the hint for a metadata to be a map of string to string rather than just a string in itself. And taking a look, now we can see that all of those string columns or string data for metadata are now this nice map that we can go into and manipulate much more easily. And all of this was done just through a few lines of code. And that's kind of the idea behind the simplicity of autoloader. So in practice, Databricks has been using it for our internal logs pipeline to ingest 50 plus terabytes of data per day. And dozens of our customers are using it to ingest tens of petabytes so far. And hopefully you're going to be one too. We appreciate all feedback, and thank you.